Welcome to Flictronics. This is a certified technology specialist course. Here is what we'll cover in this video. We will cover how to prepare for an AV installation permanently and for live production and events. We will cover how to terminate cables correctly and test them, how to build and wire equipment racks, how to plan, pull, and protect cabling through buildings, how to mount projectors, screens, loudspeakers, and displays safely, how to set up and configure AV control systems, and to integrate AV systems with IP networks, how to set up AV for live production from truck to showtime, and finally, we will cover how to think about ongoing support and life cycle of AV systems. Today's technology specialists, their skill set is not just about networks, it's also about racks, cables, mounts, mics, projectors, and people in a room who just need this to work. Your job is to do three things reliably. Number one, turn drawings into reality. Number two, make the system stable and maintainable. And number three, keep people and property safe while you do this. The first step is to prepare for an installation. This is what separates just about works from reliable for years. Before you step on site, answer these few questions. Number one, what matters most right now? Which project is priority one and what has hard deadlines? Board meeting, opening, exam week. Number two, what is my scope? What am I responsible for? Racks only, fully integrated system, just termination and testing. How will success be measured? Working demo, full punch list, sign-off tests. What is the plan for today? Which sites are you on? Which rooms, racks, floors are in scope today? And what's the logical sequence? Infrastructure, racks, field devices, tests. Number four, do I understand the design? Elevation drawings, rack layouts, signal flow diagrams, and control pages. This also includes network diagrams, subnets, VLAN IDs, and so on. Number five, do I have everything I need? Tools, screwdrivers, punch down tools, crimpers, so on. Consumables. Do I have connectors, terminations, labels, cable ties, tape, lubricants? And also this includes docs, system drawings, IP plan, control button by button spec, and manufacturer manuals if need be. And number six, is the gear good? Open every box, check for obvious damage, and power on and do basic self-tests. Nothing unusual. The next is safety on the job site. It's everybody's responsibility, and it's non-negotiable. You're mixing power, weight, height, and chaos. Key points to follow. Follow site rules and local code. Site induction, personal protective equipment rules, hot works permits, ladder rules. Don't cut corners. Some of the personal protective equipment that you will use are hard hats, safety boots, gloves, eye protection, and sometimes hearing protection where required. And if you're working at height, you will have a harness and full arrest. It is essential that you use correct access equipment as well. Rated ladders and platforms only, no standing on chairs, tables, boxes. And it's always important to respect electricity. Lockouts, tag-out procedures where required, and never work live unless it is absolutely required and permitted by procedure. Let's move on to cable termination and how to do this right. Cable termination is the way you attach a connector or bare conductors to the end of a cable so that signal and power can pass reliably. Most AV faults at this point come back to this. not firmware, not mystery network issues. Simple terminations. Most terminations follow the same principle. You strip the cable. Your goal is to expose the conductors without damaging them. Most cables have a cable jacket. It's an outer layer which protects everything inside. They also have an insulation, and plastic around each conductor, and a shield. It looks like a foil or a braid that protects against interference. And finally, the conductors, the copper that actually carries the signal. Use the correct stripping tool for the different cable types. For coax, for example, you will use a multi-bladed stripper. For twisted pairs, shielded and unshielded, use an adjustable stripper that doesn't nick the pairs. And for multi-pairs and speaker cables, use the appropriate gauge stripper. Mistakes here can change impedance and can wreck performance, especially in RF and video. You will often see a few types of termination methods and connector types, of course. There is the direct screw-down terminations. Means the wire is under a screw terminal or barrier strip. This is often used for loudspeakers and relay contacts and simple control points. You may wrap solid conductors around the screw and crimp a spade or ring lug onto a stranded wire, then screw that down. There's the compression and captive screw. In this one, the wire goes into small removable connector, the captive screw. Tightening the screw compresses the conductor under a plate. These are common on DSPs and control processors. They are good for line-level audio control and low-voltage signals. And you have, of course, the soldered connector. Soldering is simply joining metals with a melted alloy, the solder, for a permanent electrical connection. The common AV soldered connectors are the XLR ones. Those are 3 or 7 pins. This is standard for balanced audio, mic, and line. Pin 1 is the shield or ground. Pin 2 is the hot or the positive. And pin 3 is the cold and the negative. You will also see the RCAs or the phonos, and they are legacy composite video and unbalanced audio. Quarter inch, TS or TRS. TS is short for tip and sleeve. This is often unbalanced. TRS or tip ring sleeve can be balanced or stereo. You will also find the 3.5 mil. This is often for consumer stuff, laptop, phone audio. There are 3 rules to remember about soldering. Tin the conductor and the lug. Heat the joint, not the solder. And shiny, smooth solder is good. Dull and grainy is bad. That's a cold joint. Another common type is crimp and linear compression. Crimping is deforming a metal sleeve or connector with a tool so it grips the conductor permanently. This is used for lugs on power and speaker cables, some data and RF connectors. Few examples are BNC on coax. Usually the connector slides over prepped coax. A special tool compresses it lengthwise around the cable, and the result is a strong mechanical and electrical connection. And of course, we have the insulation displacement, the RJ45 and its friends. Insulation displacement, you don't strip the conductor. The connector has sharp metal forks that cut through insulation and kind of bite the copper when pressed. This is used for RJ45 network connectors and punch-down blocks and some multi-pair terminations. For RJ45, maintain twist as close as possible to the point of termination. Follow the T568A or B consistently across the project, whether you're doing resi or commercial, and use the correct crimp tool, not pliers. So how do you test those terminations? It's of course important to test as you go. Use a multimeter for continuity and shorts, and an appropriate cable tester for RJ45, pin-to-pin mapping, split pairs, open shorts, and so on. It's important to catch termination faults before the rack ships or the ceiling closes. This saves time later. Let's move on to the fundamentals of rack building. A rack is a framework that holds, powers, and interconnects system electronics. You will spend a lot of your life standing in front of one. Think about usability, stability, cooling, signal integrity, and serviceability. Let's talk about some layout priorities when it comes to racks. First up, ergonomics. Put user-facing devices at reachable height. Patch panels, EQs, media players, front panel controls. Background devices can go higher or lower. The accessibility range, especially for accessibility standards, is roughly 380 to 1220 mil. That's about 15 to 48 inch from finished floor for regular interaction. For weight distribution, heavy gear should be placed low in the rack. Try to avoid a top-heavy rack that can tip, and consider rear rails or shelves for heavy 1-2 RU devices to reduce front panel torque. For RF and IR receivers, wireless mics for example, those need antennas in good RF location, so don't hide them behind solid metal, and use front mount kits or remote antennas. IR receivers need line of sight or use IR distribution systems in that case. Let's move on to heat management. As I'm sure you know, electronics turn power into heat. Racks, unfortunately, concentrate that heat. There are three patterns that I want you to pay attention to: convection cooling, evacuation cooling, and forced air cooling. Convection cooling relies on hot air rising naturally. Vents at the top, intake at the bottom. It's okay only for low power systems. Evacuation cooling relies on fans to suck hot air out of the top or rear. Cool air is pulled in at the bottom, front. And finally, forced air cooling. Fans push cool or chilled air into the rack, usually from the bottom front. Hot air exits through the vents at the top or the rear. The best practices is to keep vents clear. Don't block equipment vent holes with other gear, and use blank and vented panels to create a clean airflow path. Group high heat gear and manage it consciously. Now let's talk about signal separation inside that rack. Your goal is to keep strong, noisy signals away from weak, sensitive ones. Here are some typical groups that you will see in a rack: mic levels, line levels, video signals, control data, RF, loudspeaker lines and AC power, and dimmed lighting. So how do you do this? Within the rack, you separate bundles by signal type and strength, and avoid running power parallel to mic cables for long distances, and cross different signal types at 90 degrees where they must intersect. The workflow of assembling a rack is straightforward. If it's flat packed, which often is the case, assemble the frame first. Step 2. Install mechanical accessories, power strips, PDUs, cable managers, fans, blank panels, and vent panels. Number 3. Document serial numbers, asset IDs before the gear goes in. Then fit the rack ears and the shelves to equipment. Preferably, lay the rack on its back on a padded surface for loading. Now it's time to look at the drawings and mount the equipment according to the elevation drawings. Heavy gear first at the bottom as we agreed and work upwards. Now it's time to wire the internals. Choose appropriate cable and termination for each connection. Maintain signal separation as we just said. Cut cable to length with a bit of service slack, not coils everywhere. The sequence is as follows: terminate, label, dress, and tie. Then install the AC power as per design and local code. Multiple circuits if needed, proper grounding and bonding. And finally, the closeout is for continuity and functional tests. Do that on the bench before the rack leaves the workshop. For those working on site, there are a few things that we got to talk about. Cable handling and pulling through a building. Some of the key terms that you will encounter. A raceway is any enclosed channel built to carry cable, conduit, ducts, etc. Conduit is a circular tube or can be metal or plastic that encloses cable. A cable tray or a ladder is an open support system for many cables that's usually overhead. Find it often in data centers and server rooms. A junction box is a box at the end of a conduit for terminations and splices. And the pull box is an intermediate box used to pull cables in stages. There are 3 metal conduit types that are common on sites. Electrical metal tubing, that's EMT for short. It's thin wall, easy to bend, not for harsh physical environments. There's the flex type. This is for movable or vibrating equipment. And the rigid metal conduit. This is thick threaded maximum physical and EMI protection. Every conduit has a maximum amount of cable cross-section it can carry. This is expressed as a percentage of the internal area. Typical guides that will help you on site. For one cable, it's up to 53% roughly of cross-section. If it's going to carry 2 cables, it's up to 31% total. If it's 3 cables, then it's up to 40%. So you are to look up each cable's outer diameter, compute cross-section area or use tables, some areas of all cables planned for that conduit, and compare to allowed fill for that conduit size and number cable. If you ignore this, you will fight the pull and you may damage cables on site. So how do you pull cables? So you gotta prepare to pull those cables, and before you touch a fish tape, there are a few things that I would like you to do. Study the cable riser diagrams and floor plans. Physically locate boxes and conduit points, floor, wall, ceilings, and confirm which boxes are yours and which belong to other systems, fire, security, data, and plan your bundles. Group cables by signal type to maintain separation, of course. Mics together, speakers together, and power separate, and so on. You start by tying multiple cables and the pull string together with a tape or grip. Keep the bundle smooth and tapered to avoid snagging. And don't forget labeling. Temporary IDs before pulling. Tags at both ends. Permanent labels after terminations. And follow a run sheet or naming schemes. Rack 1, video-out 3, etc. The tools that you're going to use to pull cables are fish tapes, draw wires. These are long steel or fiberglass tape with a hook and a lubricant, an approved cable lube to reduce friction when needed. The process is as follows. Number 1. Feed fish tape from far end of conduit until it appears at the near end. Number 2. Attach, pull string or directly attach the cable bundle. Number 3, pull smoothly with someone feeding cable straight into the entry. Number 4, use pull boxes to break long or bend heavy runs into stages. And number 5, rewind fish tape immediately. Don't let it tangle. A couple of things that I would like you to pay attention to as you do this. A. The pulling tension. Too much force stretches conductors, especially twisted pair and fiber. Good specs give a max tension. In practice, experience and feel matter often. If it feels like a tug of war, stop, back off, and reduce friction or reroute if necessary. The second key thing is the bend radius. So the minimum bend radius is roughly 4 times the cable diameter. Check the manufacturer limits though. Tight bends equals changed impedance, equals attenuation or permanent damage. If the cable jacket wrinkles or bulges at the bend, it's overbent. Replace it immediately. When you are on site, observe old safety rules and PPE and coordinate with other trades, electricians, HVAC, ceiling grids, on timing, of course. And pull from spools mounted on a spool holder, not loose on the floor. And use color coding where it makes sense, but never instead of labeling. Add realistic slack for terminations and services. And keep communication between pullers via radio or phone, and feed cable straight. Avoid twisting and crossing at the entry. And if a pull jams, back out. Don't just pull harder. And keep workspace clean. Remove burrs and sharp edges in boxing. Let's talk about mounting and how to mount components safely. Mounting is essentially structural engineering in miniature. If it fails, it's your problem. Understand load, safety factors, and failure modes. The load limit is the weight where the component, mount, bolt, etc. will structurally fail. The safe working load or working load limit is the maximum weight you are allowed to hang in normal use. And the safety factor is the margin between the safe working load and actual failure. A common rule in AV is to design mounts to support 5 times the equipment weight. For example, a speaker plus bracket equals 50 kilograms. Design mount systems for at least 250 kilogram capacity. There are a few failure modes that you will encounter. Shear load, bolts or anchors being cut sideways by gravity. Tensile load is fastener being pulled straight out, stretching until it fails. Pull out is the anchor literally ripping out of wall or ceiling. And shock loading, sudden extra load, a person grabbing the display, small impact, seismic event, something like that. It's always important to mount heavy equipment to structural elements or proper blocking, not just drywall. The mounting workflow is as follows. Before drilling anything, confirm the device location from the design, the height, the horizontal position, and the viewing lines. Step 2. Inspect the structure. Find studs, beams, or pre-installed blocking. If unsure, consult structural drawings or a structural engineer. Step 3. Review manufacturer's mount instructions in detail. Step 4. Assemble mount hardware on the ground first. Step 5. Secure the work area, clear furniture, set barriers, and protect surfaces. And one final tip. Use rated fixings that match the substrate, the concrete, whether it's masonry or steel or timber. Let's talk about projectors for the sake of accuracy and stability. There are a few key factors that you need to take into account. The throw distance, which is the distance from lens to screen. The lens ratio, for example, 2.0 to 1 means distance equals 2x the image width. The orientation, that means is it front, is it rear, table, ceiling, inverted or not. You can use this formula to calculate the projector height. So for example, if you want to achieve a screen width of 3 meters, a lens ratio of 2 would get us to mount the projector at 6 meters. So if you want to get a 3-meter screen width with a lens ratio of 2.0, then the projector would need to be 6 meters away from the screen's surface. When you mount projectors, use correct ceiling mount or bracket. Set elevation and horizontal aim so image lands squarely on screen. And adjust projector settings to match orientation, front or rear, ceiling or table. And an important one that lots of people forget, do a vibration check. Rest your hands on the structure while the HVAC and normal building systems are running. If you feel vibration, expect image jitter then. Solve it. Different mount points, anti-vibration hardware, or relocated projector if need be. And when you are building projector screens, don't block alarms, thermostats, outlets, and switches. Ensure retractable screens, clear whiteboards, ledges, and furniture. And for motorized screens, set upper and lower limit switches so the fabric doesn't over-travel. When you're specifying or installing loudspeakers, it's important to use ones that are rated for ceiling and wall mounting when flying or suspending. Use the appropriate hardware, yokes, rigging points, rated chains, and wires. And for overhead mounting, consider seismic restraints where required by code. And never improvise rigging with non-rated hardware, that's dangerous. For flat panel displays, wall reinforcement is often needed, timber blocking between studs or structural attachment. Plan reinforcement during construction because retrofitting is messy and expensive, and use the manufacturer's specified bolts for mesa or custom pattern. Wrong length or thread can damage the display chassis, and always confirm sight lines and glare before final tightening. After mounting, connect signal, control, power, and do some functional tests. Image, audio, control, tidy cables and secure them, and clean up all packaging and debris, and return furniture and room to a usable state. Now let's move on to control systems. Think of the control system as a specialized automation stack. The CPU or the control processor, network and serial interfaces, I/O, relays, contacts, closures, and user interfaces, touch panels, keypads, and schedulers. At the design and the workshop stage, which should be first, every control system should have a button-by-button specification for each page, state which controls appear and what they do, signal flow docs and what talks to what over which protocol. Whenever possible, configure and test control hardware in the workshop and connect test devices or simulators to verify logic, and iterate with the programmer before going to site. This will save you some time later. So how do we manage control system wiring and termination? Let's go through the common types. Common control signal types are Ethernet or over IP. That's usually twisted pair, RJ45, or maybe fiber in some situations. This is used for control, monitoring, and content transport, or maybe web interfaces. RS-232, that's typically a DB9 connector, unbalanced serial. It's a point-to-point control and often bidirectional for commands and feedback. To use it, you need to match the baud rate, the parity, and stop bits, and flow control as well. Usually the device manual tells you about this. Another common one is the RS-422 is usually DB9 or DB25. It's balanced serial. It's better noise immunity and distance than RS-232. The next one on our list is the DMX512. It's balanced multi-drop bus. It's up to 32 nodes, typically. It uses a 5-pin XLR and requires a 120 ohm termination at both ends. USB, of course, you've seen this before, it's ubiquitous. It's multiple physical connectors, A, B, C, micro, mini. It's flexible, bidirectional, and carries control and sometimes AV content. Newer generations often not field terminable. And then you got the RF control links for wireless keypads, remotes, some touch panels. Those are susceptible to interference, so always test on site. Ramp voltage ones, those are analog voltage that varies simultaneously and continuously to control lenses, lighting, etc. They are legacy, so I don't see them as often, but they still appear in some systems. You also have relays and contact closures. These are binary, it's either on or off, open, close, up, down. Those often trigger screens, power bars, relay control devices. For each of these connectors we went through, use the right connector type and pin out, follow manufacturer's pin assignments exactly as the documentation, and document every serial port, usage, and cable type. For networked control devices on IT coordination, any device that lives on the network needs a unique identifier that's called an IP or a DNS host name for best practice, an agreed subnet, network segment or VLAN, and possibly QoS classes. The practical workflow is as follows. Number 1. Build the device list, device name, manufacturer, model, MAC address, firmware, location, purpose, estimated bandwidth. Step 2. Send that to IT with clear requests. Which devices require static IPs, DHCP or DNS host names, and which VLANs or subnets they should sit on, and any ports or protocols required between subnets. IT should then return IPs or hostname scheme, VLAN IDs and switch port configuration plan, and any restrictions or security requirements. Number 4, configure each device. You can use USB, config app, or built-in web interface. Your mileage may vary at this point. And set static versus DHCP as agreed. And mark the final address and host name on the device label. Finally, in step 5, you ping devices to verify and use console commands, ipconfig, etc. or device menus to confirm network settings. Every control system has 2 layers that you need to be aware of: the software and the firmware. The firmware is the OS inside the controller and panels. The control program is the application logic for that installation. You must ensure firmware versions are compatible across controller, panels, gateways. Load the correct control program onto the right CPU and panels. And know about any hidden pages in the UI used for technician setup, passwords, timers, debugs, and make sure these are well documented. Final checklist for you when you are testing control systems on site. Confirm device locations and labels to match the design, and verify each control cable, network link, and serial connection against drawings. Power up control CPU, user interfaces, and AV devices. For each source selection button, check the correct routing happens, switchers, displays, audio, etc. And for each control page, correct controls visible for that source: play, pause, volume, lighting. And test all wall plates, occupancy sensors, IR sensors, and relay events. And exercise multi-step logic and conditional behavior, so for example power sequences, mode changes. Unlog any discrepancy for the programmer or the designer to resolve. Now let's move on to networked AV systems. Let's align with the client standards. Let's explain subnetting in plain terms. An IPv4 has 2 parts: network part, which group the device belongs to essentially, and the host part, the unique device inside that group. The subnet masks tells devices which bits are network and which ones are host. This matters for AV because subnets confine broadcasts and multicast traffic often, and you can isolate noisy AV devices from the rest of the corporate local area network. You can design where routing occurs between AV segments and others. Another concept you need to be aware of is a VLAN. A VLAN, or a virtual local area network, is a logical broadcast domain that can span multiple switches regardless of the physical location. You can use VLANs to keep AV control and streaming traffic separated from corporate data. And you can give guests access to AV services like video conferencing without exposing internal servers. And you can apply targeted quality of service tags and ACLs to AV traffic. The key point is that a device can only sit in one subnet but can share multiple VLANs, trunking, tagging from a switch perspective. VLANs are defined on every switch in the path. That's why implementation is a bit labor-intensive if you're not familiar with network automation. ACLs can be applied to restrict what gets into the VLAN or out. When dealing with network infrastructure managers, tell them the purpose. For example, it's for IPTV distribution or room control network, etc. Tell them devices and ports involved, and whether routing to and from this VLAN is allowed, and if so, to where and from where. Let's move on to VPNs. A VPN is an encrypted tunnel between networks or endpoints over an untrusted network. We use those often in AV for remote monitoring, control of AV systems, or secure UC-VC streams between sites. Note that VPNs add headers and encryption overhead, so this means that you will have larger packets crossing the network. And if packet size exceeds the network MTU, packets may be fragmented. Fragmentation and added processing can hurt real-time media quality, jitter, latency loss, all those things. So if you ever use VPN with media, confirm MTU and overhead so packets don't require fragmentation, and test latency and jitter under realistic load. And when it comes to addressing for AV devices, there are 4 patterns you will see. Dynamic host configuration, or DHCP. In that pattern, devices request addresses from a pool, from a DHCP server. It's easy to manage at scale. It prevents address conflicts, but addresses may change over time unless they are fully reserved. Static IPs, those are fixed addresses manually configured on the device. They are required when other systems must reach the device reliably and can't use names. It has more admin overhead though, so you must coordinate with IT to avoid collision. Reservations, as I mentioned in the previous note, that means the DHCP server always hands the same IP to a specific MAC address. This provides central control and predictable addressing. This is usually the preferred approach when DHCP is available. And the last pattern I want to mention is the DNS, or the domain name system. Devices are always referenced by names. It can be like room-101dsp.example.com, not just IPs. DNS server maps names to IPs, which can change transparently. Only useful if devices and control systems support using hostname. Now that we talked a little bit about install and site work, let's talk about live events. Permanent systems are one thing. Events, however, are high pressure, time-bounded, and often unforgiving. As you prepare for a live show and before the event, review system design and show requirements. Build a kit list: consoles, amps, speakers, mics, DI boxes. projectors, screens, flat panels, cables, power distribution, intercom, and accessory. Test all the gear for safety, path where required, and operation before loading. And plan your crew. How many, what skills, what licenses. Maybe you need a forklift, or maybe you need some rigging or MEWP. And of course, plan your logistics. Access routes, loading dock, lift dimensions, timetable for load-in, rigging, sound check, rehearsals, and show and loadout. Now, as you do these live events, here is the workflow. You start by loading and unloading trucks. As you do this, few safety points. Lift with your legs, never with your back. And ask for help on heavy or awkward items. Use dollies, carts, and pallet trucks. Secure loads on them. Never leave cases able to roll freely. Lock wheels or lay cases on their side as appropriate. And secure all loads inside the truck. Straps, load bars, correct stacking. When you unload, confirm you're allowed to use the unloading area. Use dock plates, lifts, or ramps correctly. And check route to venue, height, width, floor load, and protect floors and walls as required by venue. And when you gear for setup, for pipes and drapes, when you see heavy steel bases, you gotta treat them as a lifting and trip hazard, and always use at least 2 people. Secure uprights and ensure stability before adding drape. And always keep walkways clear. For sound reinforcement, place speakers in front of microphones to reduce feedback. Aim speakers at audience, not ceilings or wall. Place mics where presenters naturally stand or sit. Aim towards their mouths. Mix position at the back or middle of the room where you hear what the audience hears. And label mixer channels clearly. And power up sequence is the following: sources, processing, amps last, and power down in reverse. For projectors and screens, use the throw distance formula. Distance equals the lens ratio times the image width. Keep projectors away from audience heads to minimize heat and noise complaints, and ensure adequate ventilation around projectors. Run and tape cables or use cable ramps to avoid trip hazards. And check the correct input is selected. Image orientation, meaning it's not mirrored or inverted incorrectly. And make sure that the image is square on screen. Use physical alignment before you touch keystone. Make sure the focus is sharp across the entire screen. Walk the room and check sightlines. This is very important. As you fold screens, assemble the frame fully and lock the joints. Attach the screen fabric evenly and tension. And match the fabric type to projection mode, front versus rear, and add skirting and side drapes if required. For flat panel displays, the temporary ones, use the correctly rated stands or truss with proper rigging, and confirm stability stands on flat, level surfaces. And avoid blocking exits or circulation paths. Route and secure power or signal cables, always. Many clients and large AV estates can't maintain complex AV systems alone. This opens ongoing roles for you. Support functions can be in maintenance and repair, so fault finding, parts replacements, firmware updates and recabling, or system updates, adding inputs and outputs, new codecs, better microphones, or control changes. From your perspective, good documentation and labeling during installation makes support viable. And a well-maintained system turns into repeat work instead of one-off projects. Here is what we covered in this video. We covered how to prepare for both permanent and temporary AV installation. We covered how to terminate AV cabling correctly and test it for reliability. We covered how to design, build wire, cool, and dress equipment racks. How to plan cable paths, calculate conduit capacity, and pull cables safely. How to mount projector screen, loudspeakers, and displays using correct load and safety factors. How to wire, configure, and test AV control systems and their control protocols. How to plan and execute AV support for live production, from loading trucks to tape down. How to integrate with IT networks. And finally, how ongoing support and updates fit into the life cycle of an AV system. That's it. Thanks for watching.